Hello everyone, Manuel from Independent Physics here, and today's video is a short interview to Dennis Braun, an independent researcher from Bonn, Germany. Dennis has been working on Mach's principle and unifying inertia and gravity, and he has even helped us write in some of our videos. I will leave in the description his website where you can find his research papers as well as his PAMO conference presentation. Thank you. Thank you very much, Dennis, for being here in our YouTube channel, Independent Physics.
Yeah, thank you for inviting me.
Okay, so we are going to talk mainly about your model of unifying inertia and gravity. And I have a lot of questions which I couldn't do during your PAMO conference presentation. I know your soliton model has been covered in an interview with James in the YouTube channel of Indactica. And I have some questions for you, but before all of that, I want to ask you, what are you working on at the moment? What is your main interest at the moment?
Yes, currently I'm further developing the soliton model, and we are, me and Pavel Kroupa from the University of Bonn, are publishing a paper about the soliton model, and it is currently under review. And yeah, we're hoping that it gets accepted, and it has quite some progress compared to what I presented at the PAMO conference. And yes, but of course we're not finished yet with arriving at the final field equations, and that's what I'm currently working towards, especially getting an understanding what spin and entanglement is in the soliton model and finding the correct field equations.
All right, if it's published when this video is uploaded, I will put it in the description.
Okay.
Are you also thinking about publishing about the model of unifying inertia and gravity?
Sorry, what was that?
Are you thinking about publishing the previous paper you have about gravity and
Yes,
inertia?
I've just yesterday I got a correspondence from Julian Barbour again, and he told some people who were interested in MOND about the unification of gravity and inertia, and they also found it interesting. And once the soliton model is published, I'm taking another try with the gravity and inertia paper, and also the one about the anisotropic inertial masses in GR.
All right. Okay, perfect. That's very good news. One of the
I think
questions
the latter
about,
one Pavel will also be very interested in.
yes?
Yes, I think so.
Okay, perfect. One of the questions I have about the model is, what's the difference between your extension of Trede's ideas and Shyama's model? They are different. You told me that both don't have the problem of anisotropy of inertia, but what's the difference between them?
Yes, basically Sharma's model is a toy model uh, in which he postulated that the gravitational field obeys gravimetric equations. So instead of just a Newtonian term, they also have an induction term. And he postulated that a particle would always move in such a way that the field in its own rest frame is zero. But those two were postulates. So the field equations and the equation of motion were postulates. And he then showed that from this inertia term, from the induction term, one can derive an inertia term. This is what he showed, and then the gravitational constant. And Trader's model is a complete theory, non-relativistic, but it is complete in itself. It has a Lagrange function, and from the Lagrange function can be derived from Mach's principle, that everything has to depend on relative quantities. And then from the Lagrange function, you can derive the field equations, and you can derive the fact that the gravitational field also has such an induction term in it. So you can derive the field equations and you can derive the equations of motion from the theory itself. It does not have to be postulated. But the way inertia comes out as a consequence of this gravic induction term is the same. in both models. And so both have a scalar inertial mass, and this is not anisotropic.
All right, so you would say that Trede's model or your extension to Trede's model is a more complete theory.
Yes, exactly.
And your work particularly, how it differs from Trede's model? You made an extension of it?
Yes, first, the Trede's model was in its original version not rotation invariant, only translation invariant. And so if you you only got the inertial forces in a linear accelerated frame, but not in a rotating frame. But if you extend it, making it rotation invariant, then you also get the inertial forces in a rotating frame. And you solve Newton's bucket that it is equivalent if the universe is rotating or the bucket is rotating. And then also some things like Trader in his original work postulated the equivalence principle to derive an equation for the gravitational constant, but this is not necessary. If you do it a bit different, then you can derive the equivalence principle from the Lagrange function that Trader used.
Okay. Okay. And now, as you said, the models are not only non-relativistic, also linear. What is the difficulty to make it relativistic? Why is it so difficult to relativize all these models, classical models, unifying inertia and gravity?
Yes, in the classical models implementing Mach's principle are always based on quantities which are on the one side relational quantities, so they depend only on differences of velocities or differences of positions. And on the other side, they are Galilean invariant, or rather even a more general transformation than a Galilean transformation. It's if you shift by an arbitrary time-dependent vector, they are invariant under such a transformation. That would correspond to not a Galilean transformation, but a transformation into an arbitrary linear accelerated frame. And if you try to carry over this idea into the relativistic case, then you would need quantities which are relational, but at the same time also Lorentz invariant. And this you can do for the velocities. There such a quantity exists, but not for the positions. It is not, such a quantity doesn't exist. And also you do not want the Lorentz transformation is the relativistic form of the Galilean transformation, but you want to transform into arbitrary accelerated frames and not only constantly moving frames. And it is not clear what the relativistic transformation into an accelerated frame is. One only has the Lorentz transformation for the constantly moving frame, but not an accelerated one. And this is another part of the problem. And ultimately, one gets down to not really understanding where all this, what really goes on in relativity. If you want to ask how could such relational quantities look like, or how is the accelerated extension of the Lorentz transformation, then you end up questioning where these relativistic effects come from and how they arise in the first place. And yes, then one gets to trying to understand where this comes from, and this has to be done first.
Okay, yes, I think Jonathan Fay is working on some paper about relativizing Siama's model, so I'm very excited to see what comes out of it, what we can think about something new maybe. And one of the questions I always had, and probably many people have when you talk about the variable gravitational constant, is that when you have high potentials, for instance, near neutron stars, or so, that the local potentials are very high, your model predicts a deviation in the strength of gravity, which is not negligible, let's say, like a big, significant change to the value of the gravitational constant. And this is the gravitational constant is highly constrained in the solar system. So how does your model deal with this? It's the first question someone will tell you, like, if you have a varying gravitational constant, how does this fit to the constraints within the solar system, for instance?
Yes, one has to pay attention how this is measured. Usually, if one tries to constrain the gravitational constant, one takes the formalism of general relativity and then assumes a variable g inside of general relativity.
Mhm.
And then you get an effect at the second post-Newtonian order, which at which this deviates from usual GR, and this is constrained. But Trader's theory is a different one. It is a non-relativistic theory, and from in the first post-Newtonian order, you get the same perihelion shift as in general relativity. And the first post-Newtonian order is the only one which Trader's theory does make a prediction at, because it is non-relativistic. It is not a relativistic theory. And the perihelion shift term comes from the varying G in Trader's theory already.
Okay. Because I know that the perihelion shift in general relativity is partly at least a nonlinear effect already, right? You
Mhm.
can get, I mean, you can get the whole perihelion shift, but not all the other predictions of general relativity out of a linear theory, but it's usually attributed to the nonlinearity of general relativity, right?
Yes.
Okay. And now one of the questions that I had to ask you in this channel, it's not entirely related to your work, is what's your opinion about MOND and whether if you think it has maybe some relationship to Mach's principle, which is what I've been trying to tell people around for the past year to look at it.
Yes. First of all, yeah, I think MOND is the correct effective description of the far field or low acceleration limit of the correct theory we are currently looking for, whatever that turns out to be. And yeah, it is, I would say, proven by observation, especially after hearing the talk of Pavel Kroupa. One can directly observe that MOND is correct. And uh, so I would say that yeah, it's proven by observation.
Hmm.
And for a relationship to Mach's principle, um, yeah, it's like with the coincidence for the gravitational constant, if you call it a coincidence. You have a similar one for MOND, that is A0, Milgram's constant, is in the same order of magnitude as g times mass of the universe over radius of the universe squared. And this hints already that this A0 has something to do with the matter content of the universe and the remainder masses of the universe. So this is in the spirit of Mach's principle. And yeah, if you plug in the formula for the gravitational constant you get from all these unifying theories of gravity and inertia, then you end up with A0 is something like c squared over the radius of the universe. And there you still have this correspondence of this constant to parameters of the universe. And I think these two relations, they very strongly suggest that it has something to do with Mach's principle, or at least is in the spirit of it, because you have the relation of this A0 to the whole universe.
Yes, and it's very surprising for me how people in MOND, like Milgram, they mention Mach's principle in their papers, a possible relationship, because they know Mach's principle has to do with the universe at large and inertia. I don't think they know the whole story about Mach's principle, which is very deep, and you need to go through the literature. And then, of course, Jonathan Fay, and also you know it very well. Um, but they're also always thinking about a realization of Mach's principle in an effective way because they think MOND comes from the quantum vacuum. Somehow they think MOND comes from inertia being modified at low accelerations because you have always the quantum vacuum serving as a reference for an absolute acceleration. And they're not really talking about Mach's principle as the relativity of inertia, which is the one I think is what MOND is suggesting, because MOND is basically a decrease of inertia when you have low accelerations. And yeah, but still, in even Pavel Kroupa, for instance, is talking about when he makes some presentations that MOND has something to do with the quantum vacuum. I know that you are thinking about MOND and you have MOND in mind in your soliton model, and you expect and you hope that MOND comes out of it. Can you talk about a little bit about that?
Yes. First, I think that with the that why many people are not very keen on talking about Mach's principle, also not in the when it comes to MOND, is because still many believe that Mach's principle predicts an anisotropy of inertia because of this paper by Cocconi and Salpeter, where they investigated the possibility of Mach's principle leading to an anisotropy of inertia. But this was largely misunderstood as that Mach's principle does lead to anisotropy of inertia. It is, for example, in the book by Weinberg on gravitation, this is stated completely wrong. There it says that Mach's principle leads to an anisotropy of inertia, which is definitely not the case. In some models it does, but in others like Traders or Sharma's it doesn't. And this misunderstanding has very much made people avoid the topic of Mach's principle because they wrongly think it is disproven, while in fact it isn't. And
Yeah, it has been going on since the 70s, right? Or
yes, exactly. Yeah, since the 70s, yeah. Yeah, and for the other question, I do hope that something like MOND will come out in the far field limit in the soliton model. It necessarily has to, because otherwise it would disagree with the observations in the same way that the current theories do. So if a theory is complete or yeah, then it necessarily has to account for this A0 found by Milgrom and for the MOND phenomenology. It is a necessity given by observation.
Mm-hmm. And since we know that MOND necessarily has to be nonlinear, I first had hopes that you could get it out of a linear theory like Traders or Sciama's, but this is not possible. It makes sense that it could come out of your nonlinear soliton models, right?
Yes,
That's
yeah,
the
the
hope.
solitons are always nonlinear, so the field equations will be nonlinear anyway. And so this should not be a problem with the nonlinearity. But of course, the field equations still remain to be found. And it would it is hoped that it really comes out. And I think some hints are given by those coincidences, if you term them that, in which order of magnitude this A0 lies, and that it really has to do something with the universe at large scales.
Mm-hmm. I also remember you helped me do a video about the anisotropy of inertia in this channel, which I will leave also somewhere in the description, in which we developed this topic with all the references and so on. Okay. I will also put in the description your website. So I want to promote your website in which you have your publications and even some ideas developed of yours. And in your website, you said that you did not want to participate in the traditional academia path and, within the universities. Can you talk a little bit why? What is your opinion? Why didn't you go through the traditional process of research in theoretical physics within academia?
Yes, this is for two reasons. First, when I heard my courses in physics, the further I got towards the master courses, the more or the less convincing I found what I heard. So they were always open ends and unsatisfactory answers and stuff where I just thought this is not right or not the whole story. And one just gets an impression that one is on the wrong track. And so there was not much of enthusiasm to study something which was more and more just obviously wrong or just leading in the wrong direction. And on the other hand, I saw that there is not really much room or freedom in academia to pursue different approaches. It is just given by the standard theories, and there you can write your bachelor thesis or your master thesis or something like that on, and you have to listen to specific modules that are given to you, and there's not much freedom to choose and to go into different directions. And yeah, this was very off-putting. And also the way how it is done, it is more like an 8-5 assembly line job instead of really thinking. And uh, this all was very, very off-putting to me. And so I chose to drop out and do it independently.
Mm-hmm.
And also, yeah, there's a huge problem with authority that those people who are in power, they can basically just dictate what is done. And this is valued higher than following logic and evidence. And this is not really how science should be done. And
Yeah, of course, if you go to a department, you're expected to research what the department is researching and to follow the lines and help your professors. For instance, I'm very surprised that Jonathan Fay was able to choose freely his topic of his PhD. But he's also doing the philosophy in physics. He's not doing pure research in theoretical physics. Maybe they have more freedom in
yes,
philosophy, which is a good thing. It's a very nice thing. I'm actually reading a lot of philosophers of physics, like you have, for instance, Barbour has a little bit of a philosophy part. You have, who am I reading? John Norton I've read, or Maulin and people like this, and I think they have more freedom, and they do a lot of work on understanding the theories, even I think even better than the researchers themselves sometimes.
yes. For Jonathan, this was also the reason why he switched over into philosophy. He started with physics and then switched to philosophy because he said he does have more freedom there
Mm.
and do investigate such questions under historical points and philosophical points, and he wouldn't be able to do this in physics. This is why he changed over. So he told me, and so it very much seems like that the philosophers are more open to such questions, and I think it is also a huge mistake in the approach today's physics community takes on those problems is to push philosophy out because it really is part of physics and leads to many questions which are interesting to investigate.
Yeah, I'm always surprised that there's no subject about neither history or philosophy of physics in the courses in the bachelor or even the masters.
Yes.
Barely no one has courses like this. There should be at least one about the history or how physics was done. How do you expect people to do new physics if they don't know how physics was done through the history? And that's very important. I guess it's assumed you need to learn on your own if you want to
Yes.
succeed.
Yes, exactly. I mean, I learned very much by reading The Structure of Scientific Revolutions from Thomas Kuhn. And it very much deals with the historic developments of scientific theories and how progress was made. And this is very different from the impression one gets in academia. And yeah, as you said, it is something like that is not taught, and it would help if one would do it. But there's no such subject, and yeah, it would certainly help if it existed.
Hmm. Well, at least there are some seniors who apparently do have freedom to research what they want and do what they want, like Pavel Kroupa, for instance, obviously, but he's obviously a senior researcher, or even Milgram, who has decided to focus all his career over the past 40 years on MOND and exclusively
Yes,
on MOND. So these ones do have the freedom to do it.
yes, but there's a very interesting article from Pavel Kroupa. It is on his blog where he described his story and a story of a young researcher and how much attacks they had to endure and hardships because they went out of the circle. So it is not, it is far from clear that you can really get away with staying outside the circle. You have a very hard time then if you do it.
Mhm.
And yeah, it's very interesting to read and very enlightening.
I will leave it in the description also if I find it in Pavel's Kroupa blog. And you switched to teaching, I think. So you are teaching privately, I'm guessing just physics or what are you doing with teaching?
Yes, math and physics, and I privately teach some students uh, for in math and physics.
In undergraduate levels or
Yes, school and undergraduate. Yes.
and I guess you do them physically, but would you be willing to give also classes online in the future, for instance?
Yes, I mean, sometimes I have already done that, and usually they come to me when they are here from Bonn.
Mhm.
But I've also already given classes online. So during the lockdown time, and yeah, so I'm familiar with that, and it wouldn't be a problem.
You said you also were thinking about publishing a paper about the anisotropy of inertia and general relativity. Can you introduce in 5 minutes that we have what is it about?
Uh, yes. First, it is a translation of a trader's original work, where he showed using linearized gravity that this leads to an anisotropic inertial mass. And this the derivation is actually really simple, but it was only published in German, and so I and there were some minor errors, but they don't change the result qualitatively. And I made a translation of this one and corrected the mistakes and uh, put it into an English version of the paper. And then also added something about the meaning of the coordinate transformations in general relativity and the general covariance. Trader already hinted at this point, but he did not go further into detail. And I elaborated it a little bit more and proved his point about that. Usually, it is argued that you can get rid of the anisotropy of inertia by just because in GR you can always transform into a free-falling frame, and there the metric is Minkowskian, and the anisotropic effects are just higher order tidal effects. And if this were correct, then they would indeed be of 30 orders of magnitude smaller than what is predicted by the Hughes-Draver experiments or constrained by the Hughes-Draver experiments. But Trader already pointed out that one cannot just arbitrarily choose the frame, but one has to match it with the one that is in which the Hughes-Draver experiments are actually performed. And this is not a free-falling frame, but it is the one stationary at the surface of the Earth. And this is not free-falling, but it is accelerated. And general covariance just says that the field equations stay form invariant. So you can write them down in any accelerated frame and solve them, and you get that the description is still valid. But that does not mean that those frames are physically equivalent. So you still get a different physics if you evaluate this in a free-falling frame or in an accelerated frame. And you can see this from the inertial forces that you get. If you evaluate the equations in a free-falling frame, you don't have inertial forces. But if you evaluate them in an accelerated frame, like for example the surface of the Earth, you get an inertial force or the gravitational force. And the same also in a rotating frame. Of course, the field equations are valid in a rotating frame and in a non-rotating frame, but this does not mean that they are equivalent. You can tell whether you are rotating or not, because in the one you have the centrifugal forces, and in the other one you don't have. And so basically this argument that you can always go into a free-falling frame to get rid of the anisotropy of inertia is wrong, because the Hughes-Draver experiments are performed in an accelerated frame, the surface of the Earth, and this is where you have to evaluate the equations and not in a free-falling frame. And if you do it in this accelerated frame, you get an anisotropy which is 13 magnitudes above what is ruled out by the Hughes-Draver experiments. And this is a serious problem.
The serious problem for general relativity.
Yes, and not only for general relativity, but you can show that this problem arises in all metric tensorial theories of gravitation. So it is a problem for all metric theories of gravitation. So either they have to be metric but scalar, or they don't have to be metric at all, which is what, for example, the soliton model does. This is not a metric theory, and I personally think that one has to get away from the metric theories and think about the effects which are currently attributed to space and time in a different way.
Okay, I will leave in the description your paper that is not published, but still it's you got it in ResearchGate, and you helped me doing a video about this, covering a little bit of the historical aspects with also it was Dicke's opinion about the topic, right? Okay, so we have 3 minutes left. We can finish here. It's good that we finished with all the questions. So thank you very much
Yeah.
for all these insights. I think it's great to be like a complement to your presentation, PAMO conference presentation. And yes, of course, the topics you cover, I'm very interested on them. And in my channel, as you can see, we have talked about things that I'm already doing videos
Mhm.
about every month or so. So thank you very much, and hope to see you're starting publishing all these things. Think you have a lot of content to publish, and with the help of Pavel Group, I'm sure you'll do it very, very good, and you will have success on that.
Yeah, thank you for inviting me and also for I learned a lot about MOND and this connections to to Mach's principle from you and um, I, I was always sure that MOND is the correct way to do it, but that it has that it already has so much descriptive power. I wasn't aware of that, and so thank you too for giving me this the insights into MOND, and I'm far more convinced of it now than I was like 2 years ago.
I've been insisting for, for a year on it. Yes. Thank you.
Yeah.
Thank you very much. So see you next time, hopefully in the next PAMO conference or maybe in Germany, who knows? And wish you best luck for with your research.
Yeah, thank you, and I'm looking forward to it.
Okay, ciao. Thank you.
Bye.